Okay, let's take a look at this question. So here we have manganese ion, MnO4 2-, which is a common oxidizing agent used in organic reactions such as to oxidize alcohol that produce carboxylic acid. And then in acidic condition, manganese ion easily undergoes a disproportionation reaction that produces permanganate ion, MnO4-, and a precipitate of manganese 4 oxide. So this proportionation reaction means that a chemical undergoes oxidation and reduction simultaneously. So let's say, from one reactant producing two products, and each product is like half reaction, oxidation and reduction. And then here we also have the data of reduction potential for this one and this one. So now let's take a look at the question A, which is to write down the balanced chemical equation of the disproportionation reaction of the manganese ion. So here I'm going to divide the disproportionate reaction into each half reaction, so oxidation and reduction. So I'm going to write here. So the first one is, let's say, oxidation, and this oxidation takes place at anode, and I'm going to write the reaction. So let's say let's analyze the process that is happening here. So basically we have manganese ion, so I'm going to write here manganese ion over here, and then these manganese ions produce two different chemical species. The first one is permanganate ion, so MnO4-, and the other one is a solid precipitate, which is manganese 4 oxide. So here MnO2. Now we are going to analyze each oxidation number because we want to know like which one is the reduction and which one is the oxidation. So let's start for this. So the oxidation number of oxygen is -2, so we have 4 over here. So we have like -8, and then here the total should be like -2. So Mn over here should be +6. And then let's take a look at the permanganate ion. Here, the oxidation number of oxygen is also -2. So we have like -8 over here. And then the total should be -1. So in this case, the manganese here should be +7. And then here, the oxidation number of oxygen is also -2. So here we have like a total of -4. And then it is a natural chemical species, so in this case the manganese here is like +4. Now we can then decide which one undergoes oxidation and which one is the reduction. So for example here in the beginning we have manganese +6, and in the permanganate ion it becomes +7, so it's like an increase of oxidation number. So in that case we have oxidation. So I'm going to here, this one is oxidation. And then from manganese 6 +6 becoming manganese +4, so there's like a decrease in the oxidation number of the manganese. So that one is the reduction. So I'm going to add here the manganese becoming manganese 4 over here, and that is for the reduction. So in that case, now we can divide the half reaction. So for the oxidation, we have here the, let's say, the manganese, the manganate ion here, and then the product for the oxidation is the permanganate. Okay, here, and the result is MnO4 minus. So we can see that the number of the manganese and the oxygen for both sides are already the same. So we just need to balance the charge. On the left we have -2, and then on the right we have like -1. So we add 1 electron over here so that we have like -2 for both sides. And the next half reaction is the reduction, and this happen at cathode. Now let's take a look. So we have like manganese ion, and then here we have the product, which is manganese 4 oxide. Okay, now we can see that the number of the oxygen for both sides is different. So we have 4 on the left side, we have 2 on the right side. So we add water to balance the number of the oxygen. So in that case, we add like 2 water. So in total, we have like 4 oxygen each. But because we add 2 water, then we have an additional surplus of hydrogen here. So let's say this is in acidic condition. So we add 4H plus over here so that we have like 4 hydrogen each. And then the next one, we are going to analyze the charge. So on the left, for example, we have like -2 and +4. So we have like +2. And then on the right, we have like 0. So if we want to balance the charge, then we have to add a +2 electron over here. Now, because the reduction oxidation involves 2 electrons, it means that the oxidation number here should also be like 2 electrons. So we're going to multiply the oxidation number by 2. So here we have like 2, and 2 electron here. So we end up with the same number of the electron. So in that case, then we can have the total reaction. For example, in this case, we can then cross the electron because the number is already the same. So in this case, we have 3 manganese ion, and then 4H plus, and then here we have permanganate ion, and then we have manganese 4 oxide, and then water. Now, after we have the total reaction, we have to check whether it is already balanced. So, for example, here we check for the number of the manganese. On the left we have like 3, on the right we also have 3, so it's balanced. And then for the oxygen, here we have 12, here we have 8 plus 2, 10, and so on too. That's also 12. And then we have like 4 hydrogen over here, and also 4 hydrogen over here. And then for the charge, here we have -6 plus 4. So here we have like -2, and this is also like -2. So it's already balanced. So the balanced chemical equation is this one here. Now let's take a look at the question B, which is to calculate the standard reduction potential for standard cell potential for the reaction in A. So I'm going to write down the formula to calculate that. So we have standard cell potential, and this can be calculated using the cathode minus anode, or reduction. I'm going to write reduction minus oxidation. And then what we have to remember is that we are using, for this calculation, we are using the reduction potential SE, so we don't change the sign. So for example, which one undergoes reduction at cathode? It involves MnO4 2 minus and MnO2. So we are going to use the potential reduction related to that, which is this MnO4 2 minus MnO2. And then for the anode, for the oxidation, it involves MnO4 2 minus and MnO4 minus. So in that case, we are going to use the reduction potential for that one. So not for the reaction, but like the initial reduction potential value, which is of course reduction. So here we have like this. Okay, so now we put the value of each. Here we have 2.272 volt minus this one. Okay. So this is a positive value, which is telling us that this is a spontaneous reaction, and this is a galvanic or voltaic cell, 1708 volt. Now let's go to the question C. Calculate the E cell for the reaction in pH2 if 75% of the 0.1 molar solution of manganese iron has been reacted. So for this, we are focusing on the total reaction. So that's to make it clear, I'm going to write it down, the total reaction that we have already balanced this equation before. So this is an acidic condition. Okay, so this is very important to be able to write down each phase of this chemical species, because for example here the solid precipitate, we are not going to put these in the calculation of the reaction quotient, or let's say at the equilibrium constant formula, and this one also not. So if I write down the Q here, that should be then the concentration of the MnO4 minus, and then divide it. I don't forget the 2 because we have a coefficient over there. Divided by the manganese iron concentration, and here we have like 3, and also H plus over here. This is 3. Oh, sorry, 4. Okay. So here we have pH 2. So in that case, so pH 2 pH 2 means that the concentration of H plus is 10 to the power of minus 2 molar. And then we have information that 75% of the 0.1 molar solution of manganese iron has been reacted. So it means that if I'm writing this as an equilibrium reaction, so let's say I change this here. If I'm writing like the ICE table, so let's say the ICE table based on this reaction. So at initial, we have 0.1 molar solution of the manganese iron. I'm going to write here. And then 75% of this has been reacted. It means that we have 75% times that one, so times 0.1 molar. Okay. So what you want to, let's say, know the concentration is to 1 at equilibrium. Okay. So let's say here, this equals to 0.075, which means that at the equilibrium we have 0.1 minus this value. So here we have 0.025 molar. Okay. And then if that reacted, which means that the product of the permanganate ion, MnO4 minus, so here we have like, this is minus, right? Because it's like decreasing because it's reacted, but here we have like plus. So we are going to use the coefficient here, 0.05 molar, okay? So in this case, we have 0 point, which is 0.05 molar. So at equilibrium here, we also have this amount, okay? Now, the amount of the H plus over here at the equilibrium is actually this one. So here is the amount of the concentration of H plus at equilibrium, or at final reaction. So in that case, we then can calculate the Q, or I just waited it down, Q, the concentration of MnO4 minus, so we have 0.05, and then here we have manganate, which is 0.025, but it's like 3, and then we have H plus 10 to the power of minus 2, but this is like 4, so we are going to calculate this, okay? That is the Q. So in that case, we are going to calculate the E cell, which is using the Nernst equation. So E cell, this is not a standard because the concentration of the species here is not 1 molar, it's not 1 atmosphere, for example. So here we have, we need the standard cell potential. So the cell potential that we have calculated is we have this, and then the R that we are using is this value, and then the temperature should be in Kelvin. So let's take a look. What is the, okay, let's assume this is room temperature, so we have 298 Kelvin. And then here we need the N, which is the number of the electron involved in the reaction, and then we know that it was involving 2 electrons. So this one here should be 2, and then the Faraday constant, and then the ln Q. So here we have 1406 volt. Okay, and then let's take a look at the question D. Calculate the number of moles of electron which is involved in the disproportionation of 500 milliliter of 0.1 molar solution of manganese ion. So the mole of manganese ion we can calculate from the multiplication of volume and molarity. So here we have 50 millimole. And then if we take a look for the electron here, okay, so from the reaction, so let's say if I write it this base, this is 2 minus manganese ion. And then if we like calculate or compare with the mole of the electron, we know that we have like 3 based on the balanced chemical equation, and then we have like 2 moles involved. So in that case, the mole of the electron should be 2/3 times 50 millimole. So we have like around 30 point. Okay, so this is the mole. Or if we change it to moles, then we have. Okay, let's take a look at the question C. So which compound is more stable to keep, the manganic acid or barium manganate? So let's take a look. Here, manganic acid. So we have manganate ion. So here we need like 2H plus to form acid. So let's say I'm going to write here. And then another one is the barium manganate. So this is barium 2 plus. So in this case we have barium manganate. Okay, so now let's take a look. Here we have acid, and the other one is salt. So this one is acid, and this one is salt. So we can say that the barium manganate will be more stable because it has like ionic interaction here, ionic bonding. So here we have like ionic bonding, which is this will be stronger compared to the bonding in the acid. So this one should be more stable.